Welcome to Binary Star, a channel demystifying mathematics. And there are few areas of mathematics as misunderstood as statistics. Many people would think of it as magic or art of making up vague prophecies. But in fact, statistics is part of mathematics. And as any part of mathematics, is based on rigorous reasoning and proof. So you might ask, how is it possible to use experiment and data to actually prove statements about our world? I'll show you this in an example scenario. I want to make it clear that it's an intentionally artificial one, as I wouldn't want you to have any preconceptions about the outcome of the experiment. This is James, and this is the Lucky Dice casino down the road. James is not someone who gambles away all his salary. He only plays low-stakes games. He sometimes gets lucky and wins some money, but more often he would come home with a small loss. But last night he came back from the Lucky Dice furious. He spent the evening playing a spinner game and he lost £200. He suspects the game parlor owner rigged the spinners as he couldn't remember losing that much money on one night. So let's take a closer look at the game James played. So this is what the device looks like. You pay £2 to play and then you spin the spinner. When the wheel stops, you're paid the amount shown. There's no apparent reason why one should be more likely to lose money than to win here. The design appears to be perfectly balanced. All 5 arcs of the spinner are of equal length, so 20% of the time the spinner stops at £2 sector and you break exactly even. 20% of the time you win the grand prize of £4, so £2 net gain, which perfectly balances out with a £2 net loss 20% of the time when the spinner stops at the 0 sector. The remaining cases, 20% of the time the spinner stops at £3 sector, you net gain £1, and 20% of the time the spinner stops at the red 1, you get £1 back of your £2 stake, net loss of £1, again perfectly balances out. Therefore, if there is no other intentional or unintentional bias against the player, we should be on average even. In that case, if James lost £200 in a single night, the game does have to be rigged, doesn't it? But wait, we can't jump to conclusions so hastily. This wasn't exactly a controlled experiment. It's what James feels after a very unlucky night. So we need to ask him 2 key questions. Firstly, James, were there any nights before where you won a similar amount of money? Well, it's easy to suspect foul play if you lose a lot of money, but credit your luck for similar wins on other nights. That might have been the case there. And secondly, James, how long did you play tonight? We see the answer. It looks like the stop condition itself had bearing on the result. Maybe if James had more money to gamble with, he would have recovered from his losses. So to rigorously determine whether the game is biased against the player, we need to send James back to the Lucky Dice casino to perform a controlled experiment. But first, we need to plan this experiment. To plan the experiment, we need to decide on 2 things in advance. Firstly, how long are we going to play? So how many times will we ask James to spin the wheel, or how much money is he going to stake? This is called the sample size. And secondly, we need to decide what we're going to measure in our experiment. Is it the number of times the spinner ends on 0? Is it the number of times we end the game on a red sector? Or is it maybe the net loss for James after the whole session, or something else? This is called the statistic. There are no wrong answers to these questions. But what is important is to answer them clearly and unambiguously before the experiment commences. So let's decide on the following. We'll give James £40 to stake on this game and ask him to play exactly 20 spins. And we will measure his total net profit or total net loss over these 20 games. To make it clear, we only care about the magnitude of the loss. So a loss of £15 is considered more unlucky than a loss of £14. We're not interested, for example, in James losing exactly £10 and saying, oh, what a coincidence, it's such a round number, it definitely proves some bias. So it's magnitude of total net loss that is our statistics. So are we ready to send James back to perform his experiment? Well, not yet. Let's stop to think, what would the likely outcome of this experiment be if the spinners were in fact perfectly fair? This is called the null hypothesis. When performing any statistical test, we always assume the so-called null hypothesis until we're proven otherwise. This null hypothesis claims that the world is perfectly fair, behaves according to the mathematical rules of probability, and if any strange, unlucky, or unexpected event takes place, it's just a total coincidence. In our case, null hypothesis states that the spinners are perfectly fair, with each outcome happening with equal probability, and each subsequent spin result does not depend on the results of previous spins. So before we send James to face the spinners, we will construct our model of a perfectly fair spinner. Actually, we need 20 of them to play 20 games and simulate the whole experiment. So here is our perfectly fair 20 spinner collection. Each of them is programmed to give each result with exactly 20% probability. So let's see what happens when we spin them all. And we end up with a net loss of £4. Each spinner is perfectly fair, they're independent of each other, but that does not mean that over 20 spins they'll always balance each other out perfectly. What this confirms is that if James visits the casino and returns with a small loss, say £4 net, it's not a proof of any foul play. As we can see, this is exactly what happened with perfectly unbiased devices the very first time we run the experiment. So let's spin these 20 first spinners again and see what happens this time. And this time, we registered a £7 profit. Sometimes we'll win over 20 spins, sometimes we'll lose. I'll perform this experiment a few more times, recording the results on a bar chart. Each entry on the bar chart represents an experiment of 20 perfectly fair spins. So let's run it a few more times. And we already see that very few experiments made with these unbiased spinners end up with breaking exactly even. They're represented by the red bar. It looks like it's between 5 and 6% of all experiments. But interestingly, all of the experiments end up with a net profit or net loss reasonably close to zero. We don't get outliers very, very far away. We don't have sessions with £40 or even £30 net gain or profit. Let's speed up our simulation a bit and let's see what pattern would emerge. And we already see a very interesting pattern emerging. The shape. This is probably the shape most commonly associated with statistics, and it's coming up out of a completely arbitrary experiment. In the latter part of the simulation, it almost stopped changing. Yes, the scale of the y-axis changed to fit the whole chart on the screen, so the bars were in fact getting taller, but the overall shape stayed almost exactly the same for the second part of the simulation. Secondly, only about 6% of all the experiments ended up breaking exactly even. Yes, it was the most common result, but not by far. On the other hand, when we widen the range a bit and see how often we end up with a profit or loss within £5 of breaking even, that's over half of the time. And over 90% of the time, we end up with a profit or loss within £10 of breaking even. So while breaking exactly even is not very likely, being close to it is what happens almost all the time. Let's look at it from a slightly different perspective now. 47% of the time, we end up with a loss. But most of these times, it's a very small loss. If we look at these very, very unlucky sessions where we lose more than £10 in 20 spins, that's below 5% of all the experiments. And very, very rarely we're going to lose more than £20. That is a genuine outlier. That almost doesn't happen. So this gives us a framework to interpret the results when James comes back from the lucky dice after his actual experiment. If he loses a couple of pounds overall, we see it quite often happens by chance, so that would prove nothing. In fact, that would suggest that probably the spinners are fair after all. On the other hand, if James loses more than £10, he's either very unlucky or there is indeed something very wrong with the game. If he loses more than £20, we can be virtually sure that there is some foul play going on. Let's just pause here to investigate one more question you might want to ask here. Maybe these 100,000 experiments resulted in this distribution of outcomes by sheer chance. Maybe a different set of 100,000 experiments would give us a completely different distribution, completely different shape. So to answer these concerns, we'll perform 100,000 null hypothesis experiments again. For that, I'll build a brand new collection of 20 perfectly unbiased spinners. Here they are. And let's spin them, see what the result is. This time we start with a net loss of £3, not £4. Slightly different start to our experiment. And our second experiment ends with a gain of £4. Slightly different start. Let's record the results on a perfectly new bar chart. And let's run the experiment a few times more. And let's speed up. This time we'll do it slightly faster. We'll see the start to the experiment is slightly different. But when we speed up and perform more runs, the overall pattern emerging appears to be almost exactly the same. Indeed, the shape is our old familiar shape from the last experiment. Once again, just over 6% of the experiments are breaking even. It's the most common result, but not by far. And once again, just below 47% of the experiments end up in a loss, but it's quite unlikely to lose a lot of money. You can see the numbers are almost exactly the same as in the previous experiment. And this is the fundamental reason why statistical reasoning is viable at all. While we don't know what would happen in a single experiment, we can tell to the nearest percentage point or even further what the distribution of the results is going to be over thousands of experiments. This is one of the most fundamental reasons why statistics works. So now we're ready for the actual experiment. It is now time to send James to the lucky dice armed with £40 to settle the matter once and for all. Right, James is inside the lucky dice casino now, and this is the very spinner he faces. He doesn't know whether it's fair or biased against him, but he has the experiment planned carefully and he's going through with it. He's going to find out. First spin. Spinning the wheel and a loss. At this stage, James is probably already thinking it's biased, but that was not the statistics. Not the first spin. The total only counts. And we can see that the next spin actually caught him up a bit. It was £3 win. Well, now it's 1, but it's still not 0. So let's continue playing this game as we agreed to 20 spins. So we have to go through it and see what's going on. We can see a variety of results. At the moment, James is behind, but see, he won a grand prize at some point. So maybe this spinner is not that bad after all. We're halfway through. And a few more spins to go. We have to go through 20. We can't stop earlier. That was the way we planned our experiments. We can see some of the times we're winning, some of the times we're losing. We have a full range of outcomes. Okay, 3 more spins. And last one. And that's it. £40 were staked on the spinner, and in these 20 spins, James managed to win back £23. His net loss is £17. Obviously, he's not happy with the outcome, but could it happen if the spinners are perfectly fair? To decide on that, we need to return to the results of our null hypothesis test. Fortunately, we still have our handy bar chart. On his trip to the casino, James lost £17 over 20 spins. We can see on the chart that being so unlucky is really unlikely if the spinners are fair. In fact, only the red bars, about 1 in 240 experiments, represent an outcome so unlucky or more unlucky than what really happened. The blue bars, nearly all the experiments, represent those situations that would be luckier for James than what has actually happened. Performing a single experiment and ending up with a 1 in 240 unlucky event would be a massive coincidence. But if the spinners are fair, this is exactly what happened. The only other option is that the game was indeed biased against James. So what we have managed to rigorously prove is that one of these two statements is true. Either we have just witnessed a 1 in 240 rare unlucky coincidence during our single experiment, or James was right and the game was rigged against him. So we're done, aren't we? Well, if you are familiar with proofs in other areas of mathematics, you might say here, wait, a proof should be watertight, based on rigorous step-by-step logic with no room for a random, rare, unlucky event that would invalidate it. But are you really sure about this? Why don't we now look into some examples from the history of mathematics together? The four-color theorem, a problem which was already of interest to 19th century cartographers. Is it possible to color any map with just 4 colors in such a way that no 2 adjacent regions share a color? And the first proof of that theorem was produced in 1976, and that proof required checking over 1,000 cases which had to be done individually by a computer. And we're talking about the 1970s. Checking by computer meant many hours of processing time on a supercomputer. Could the mathematical community back then be really sure that the author didn't make a mistake when interacting with it? Or even that an extremely rare random electrical interference event didn't cause the calculation to go wrong? Computing time was expensive back then, so the program couldn't be rerun or verified multiple times. So in fact, this proof only showed that one of these two statements is true. either the four-color theorem is indeed proven, or something went wrong when performing the calculation. Granted, the latter is extremely unlikely, but it's exactly what I was talking about, a random, rare, unlucky event that would invalidate the proof. Well, you might say this example was an extreme one, the first computer-assisted proof in history of mathematics. So let's take instead one of the most famous theorems in mathematics, which almost everyone knows about. Fermat's last theorem. This theorem originates in the 17th century. It states that this equation does not have any solutions where x, y, z are positive whole numbers and n is 3 or more. A proof was not found until 1995, when an English mathematician, Andrew Wiles, solved this centuries-old riddle. But can we be absolutely sure that he actually did it? His original main paper, published in the Annals of Mathematics, is 109 pages long. It references other cutting-edge results of similar complexity, and the mathematics it contains can be understood only by a few specialists in the field. It's not bedtime reading even for a graduate in maths. Is it therefore possible there is a mistake or gap somewhere on these 109 pages, or in one of the referenced results? Given how famous Fermat's last theorem is, Wiles' paper was read and checked by many mathematicians, but given its complexity, it's still possible, though extremely unlikely, that they all missed something. Granted, it's nowhere near 1 in 240, probably like 1 in billions, but it's still a random unlucky event that could have happened and invalidated the proof. Well, historical digressions aside, let's return to our example. In our experiment, we helped James establish that the game spinners were indeed biased against the player. Okay, unless they weren't and a random, rare, unlucky event has just happened in the experiment. But I hope I've managed to convince you that this last clause is not as ridiculous as it initially sounded. It's in fact completely natural in any area of mathematics. But statistics is even better, in a way, because in statistics we're explicit about it and we state the probability of such an random, unlucky event. This probability is called the p-value of our statistical proof. The p-value in our example is 0.0042. The event is unlikely but still possible. So it's a weak proof. Traditional mathematical proofs are much further to the right on this scale, but they're still somewhere on it. If you think about the probability of 1 in 10 to the power of 20 on the right of this scale, it represents an event that probably wouldn't happen even if every human on Earth performed an experiment every second for their whole lifetimes. Do we not think that probability that some complicated tens of pages long cutting-edge mathematical proof read by only the author and the peer reviewers contains a mistake is to the left of this point? And while the example proof has an unconvincing p-value of 0.0042, we can design statistical experiment in a way that if the hypothesis tested is indeed true, the p-value would be at 1 in 10 to the power of 20, or even further to the right on this improbability scale. But this is something for another episode. Thank you for staying with me till the end of this video. I hope it made you see statistics in a different light.